Previous session we have discussed about the derivation of this truss element 2D derivation, and we have determined the stiffness matrix for that 2D truss element. Okay, just I will recall the similarity between bar and truss. Okay, and then we'll solve it. So you can just see, for bar element there were two nodes, and each node was having 1 degree of freedom. Okay, and it was able to move in x direction only. Node 1 was able to move in x direction, and that displacement we assumed as u1. Node 2 was able to move in x direction, that we say it as u2. Okay, these were the displacement associated with that nodes. Okay, uh, and if we recall the stiffness equation, K stiffness matrix for that element is A1 E1 by L1, 1 minus 1 minus 1 1, and the displacement associated with it, with this bar element, where U1 V1, sorry, U1 U2 V1 V2, that we had written. Okay, so displacement matrix for that was Q is equal to U1 U2, force, nodal forces F1 and F2, force in at node 1 and force at node 2, and the equilibrium equation K into Q is equal to F. Strain is B into Q, and B matrix, that is strain displacement relation matrix, was 1 by L minus 1 1. Okay, and stress was determined by E into strain. Okay, so these were the things. Remember, the method of, or the steps for solving the problem for bar, truss and beam all are same. Okay, similar. Only thing is the equations goes on changes. Okay, for truss element also we have stiffness matrix, also we have strain displacement relations, also we have force matrix, but the only change is the formula changes for it. We have to again solve for K into Q is equal to F. Okay, truss is having again two nodes, node 1 and node 2. Okay, remember, for bar element also there were two nodes, but each node was able to move in only one direction, that is x direction, and in truss they are able to move in two direction, one is x direction as well as y direction. So now each node is having a displacement of u and v, u1 v1 for node 1, that is u in x direction, v in y direction. Okay, and u2 v2 for node 2. Okay, some books they take notations like q1 q2 q3 q4. Q1 is what is nothing but u1, that is displacement of node 1 in x direction, that is what they take it as q1. Q2 is what displacement of node 1 in y direction. Okay, q1 q2 q3 q4. Okay, each have their own notations. I'll follow this notation, u1 and v1, u2 v2. Okay, next what is the stiffness matrix for this one? Stiffness matrix for this truss element is K is equal to AE by L. AE by L, instead of that 1 minus 1 minus 1 1, we are having C square CS C square C. How to remember it? I'll tell you here. We have to remember upper triangular matrix only. Upper triangular matrix, it is a symmetry matrix. Okay, upper triangular matrix only. How to remember it? See here, from considering from principal diagonal elements, you go on writing the first element as C square, then CS, C square CS. Second row, add the principal diagonal element value, it is S square, then CS S square. Once it is C square, in the second row it is S square, and again in the third row it is C square, and in the fourth row it is X square. These are principal diagonal. After C square or S square, then there is a component called as CS. Okay, I'll tell about all these terms now. Okay, what is C square and what is CS? To know this, these are terms called as cos theta and sin theta. If the books have referred the displacement as q1 q2, they might have used the notation called as L and M. L is nothing but cos theta, M is nothing but sin theta. Okay. What is theta? See this very carefully. Remember it. Theta is the angle made by that element at its local node 1, measured in counterclockwise direction. See here, this is the element. Okay, and for this element local node 1 is this one. At this point, what is the angle made by this element when measured in counterclockwise direction? This is the definition of theta. Okay, if you draw the whole component in 1:1 scale and just keep a protector here, okay, why we need to give the thorough definition of this theta is, you can also put a protector, keep your protector here, and also determine theta here. Now you can also say theta is the angle made by this. Okay, so while doing the derivation, the formula was derived in such a way that theta is this angle made by that element at its local node 1 when measured in counterclockwise direction. Okay, when measured in counterclockwise direction. You can use trigonometric relations to get the value of theta and all. Okay, if theta value is given in the problem, that is well and good. Okay, if not, you have to use trigonometric relations. Next, what are the nodal displacement associated with it? Q matrix for this truss element is u1 v1, u2 v2. Okay, and what are the force matrix for it? f1x, f1y, f2x, f3y, f2y. What is this f1x? Force at node 1 in x direction, force at node 1 in y direction, force at node 2 in x direction, force at node 2 in y direction. Okay, these are the force matrix. Next, again we need to use the same equation, k into q is equal to f. Use the strain relation b into q. B is what? 1 by L minus c minus s, c and s. Okay, I think I've just forgotten to tell about this stiffness matrix. Okay, I'll again repeat it. How to remember this? This is c square cs, c square cs, s square cs, s square, c square cs, s square. Then put negative symbol for the top right 4 elements. Okay, negative symbol for it. And because this is the symmetry in matrix, all the values are same. Okay, on the other side of the principal diamond. Okay, just this is a method to remember it, that negative symbol I had done forgotten it there. Okay, then B matrix is 1 by L minus C minus S C S, and stress is E into strain. I have written at the end, you can see cos theta is, C is cos theta, S is sin theta, C square is cos square theta, S square is sin square theta. Okay, theta is the angle made by that element at its local node 1 when it measured in counterclockwise direction. Okay, these are the things that has to be remembered. Keeping into point memory all these points, we'll solve one problem. Okay, what's the problem? You can see there is a 2-bar truss shown in the figure. Determine the nodal displacement, strain, stress in each element, and also the support reactions. Okay, take Young's modulus E is 2 into 10 raised to 5 Newton per mm square. Area they have given it as 200 mm square. Okay, this is the image or this figure they have given you. Okay, now from this you need to determine all the things what are necessary to you. See from the figure the length of the element, how they are given. Okay, there is one point that is fixed here, then there is an element here, then there is another pin joint here, then the element goes continuous, and there is a fixed end at the end. Okay, means in this problem this first and last they are fixed totally. In the middle one it is free. Okay, and load is applied here. Okay, there are no forces applied at these nodes. I need to discretize this so that we can tell the numbers. Discretization, how can I do? I'll do the discretization in this method. I'll assume this as node 1, this as node 2, and this as node 3. Okay, if I take this as node 1, node 2, node 3, this is my first element and this is my second element. First element is between 1 and 2, second element is between 2 and 3. Okay, next I need to know the length of it. See here, this first element length is not given to me directly. Okay, but whereas second element length is given to me, but whereas first element length is not given to me. How can I get? I can get using this Pythagoras theorem. Okay, this length is 400, this height is 300, which is given here. Using Pythagoras theorem, I can get this value of length of the element 1. Okay, after getting the length of the element, we need to also determine the angle made by that element. How to determine the angle made by that element? This element 1 and element 2. Okay, what is the angle made by this element at its local node 1 and at its local? We'll see this while solving the problem. Okay, I have just given you the step 1, that is discretization is done. This is my node 1. Okay, node 1, node 2, node 3. Node 1 is having displacement u1 v1, node 2 is having displacement u2 v2, u3 v3 for node 3. Okay, and element connectivity table for this element 1 and 2 is written here, that is step 2. Element connectivity table, element number 1 is between 1 and 2, element number 2 is between 2 and 3. Element 1 is between 1 and 2, element 2 is between 2 and 3. See here, local node 1 and 2. Okay, that we have written. Okay, why in the first bar problem this element connectivity table was helpful at the end, that is while writing the global stiffness matrix. Now this element connectivity table is important, and its importance is seen in the immediate second step. You can see, while writing the definition of theta, we have told you theta is the angle made by that element at its local node 1. If you are measuring the angle of element 1, you should measure at node 1. If you are measuring the element 2 angle made by the element 2, then you have to measure at node 2. That is the reason this element connectivity table helps us. Okay, after step 2, if you just remember in the previous problem, step 2 we wrote only this element connectivity table and directly went to the stiffness matrix. For writing stiffness matrix, if I remember this Truss equation stiffness matrix, it is AE by L. A and E they have given in this problem. L, that is length of the element, is not given. We have to determine it. After determining that, inside the bracket matrix there is C square CS, C square CS and all terms. So those terms have to be determined so that we can directly feed it in that matrix value. Okay, so for that, immediately in this second step only, we will be writing one more table called as element table. That element table gives the information of all the length of that element, that angle made by that element, and cos theta of it, sin theta of it, sin square theta and cos square theta. This table we will write it once, and those values are directly fed in the stiffness matrix. Now see here, now I have just determined first value is length of that first element. I said we have to use this Pythagoras theorem to determine this length. This is length of this element is square root of 400 square plus 300 square. Okay, if I remember my childhood, 4 square plus 3 square, the whole root is 5. The length of this first element is 500, I think. Okay, yes, 500 mm. Pythagoras triplets, if 3, 4, 5 are Pythagoras triplets. Okay, second element, directly the length is given, that is 200 mm. 500 mm. Next, to measure the angle, we will use trigonometric relations. You can use different methods also. One method which I see it is simple and useful, that is trigonometric relations. That is theta 1. Theta 1, I said you have to measure the angle of this element 1 at node 1. This is my node 1 and this is my node 2. Okay, this is my angle theta 1. Okay, how to get theta 1? Theta 1 you can just use different relations. Theta 1, okay, you can use tan theta. Tan theta gives is opposite divided by adjacent. Tan theta is equal to opposite divided by inverse. Adjacent, you will get tan inverse, theta is equal to tan inverse of that value, and you can get it. You can use cos value also. Cos is what? Adjacent by hypotenuse. Sin is opposite by hypotenuse. Okay, those relations you use, and you use to determine the value of theta 1. Okay, tan theta 1 is 0.75. So theta 1, if I take tan inverse of it, 36.869. This is in a decimal. If you want, you can get it in terms of degree, minutes and seconds. That is in your calculator. If you just put the degree, minutes, seconds symbol, you will get 36 degree, 52 minutes and 11.63 seconds. Okay, now see this angle made by this element 2. I said you element 2, the angle has to be measured at node 2. This is my element 2 and I have to measure it at node 2. Then what is the angle made by this at this point? At this point, if I just keep a protractor like this, the angle is 0 degrees. Okay, when measured in counterclockwise direction. Okay, now the angle made by this element 2 is 0 degrees. Okay, now next we will put this element table as discussed. This element table gives the information about element number, length of that element which we have determined, what is the angle made by this, what is that cos theta of that values, what is the sin theta of it, okay, what are the cos into sin values for it, what is cos square theta of it, what is sin square theta of it. Okay, these all values are directly determined and fed in this element table. Once we feed it directly, this CS C square values are directly fed into your stiffness matrix. Okay, going to step 3, that is element stiffness matrix. Element stiffness matrix K1 is A1 E1 by L1. Okay, C square CS C square CS, S square CS S square, C square CS S square. Okay, and top 4 are negative. Top 4 right, okay, are negative. And for the first element, the displacement associated with it are u1 v1 u2 v2, u1 v1 u2 v2. Okay, now substitute all those values. Area is somewhere around 200 mm square. Young's modulus is 2 into 10 raised to 5. L is 500 mm. Okay, and then substitute it in our stiffness matrix values, C square CS and all those things from directly from element table. Feed it. Next, simplify this. That is 2 into 2 4 divided by 5 is 0.8. 0.8 multiply to each term. I have just done it. I made a mistake initially, later I just rectified it. These are the final values when you multiply 0.8 to the above matrix. Okay, next similarly I will write for element 2. Element 2 is A2 E2 by L2, C square CS C square CS S square CS S square C square CS S square. Okay, what is this displacement associated with element 2? Element 2 is displacements are u2 v2 u3 v3. Okay, u2 v2 u3 v3. Those I have written it on the top and top of the columns and side of the rows. Okay, those are just for the reference. Okay, I hope you remember those are written to make our global stiffness matrix easy. Next, if I just simplify and substitute the values of all these C square and CS values, S square values, area is 200, Young's modulus is 2 into 10 raised to 5, and length is 500. And C square CS values, if you just substitute it in this matrix, okay, and again you take a product of 200 into 2 divided by 500, the product comes out to be 0.8, and just multiply that into this final stiffness matrix value. 10 raised to 5 is kept common. Okay, substituting rest of the values inside. Okay, you will get 0.80 minus 0.800000 minus 0.80 0.80, and last row is all zeros. Okay. Now see here, after writing this element stiffness matrix, our next step is to write the global stiffness matrix. I'll recall the one more point which I had said you during properties of this global stiffness matrix. The size of the global stiffness matrix is equal to the number of nodes in that structure multiplied by what is the degree of freedom for each node. For this truss we have taken 3 nodes, 1, 2 and 3, and each is having the displacement 2, that is u and v. So they are having 2 degrees of freedom. So then our size of the global stiffness matrix becomes 3 number of nodes multiplied by 2 degrees of freedom. 3 into 2 is 6. 6 into 6 is a square matrix what we get in the global stiffness matrix. In 6 into 6 matrix, we just need to write 6 rows and 6 columns. Each row, what are those values? u1 v1, u2 v2, u3 v3. Okay, u1 v1, u2 v2, u3 v3, u1 v1, u2 v2, u3 v3. Okay, write it along with the columns along the rows also. Next, refer u1 row, u1 column. Refer u1 row, v1 column. Refer u1 row, u2 column. Refer u1 row, v2 column. Where you have to refer? You have to refer in this element stiffness matrix. Refer both the element stiffness matrix. u1 row, u1 column is present here. u1 row, v1 column is present here. u1 row, u2 column is present here. u1 row, v2 column is present here. Now if I just check in element 2, u1 is not present here. Okay, so leave it off. So u1 row, u1 v1, u2 v2 values are directly taken from stiffness matrix 1. Similarly, write v1 row, u1 column, v1 row, v1 column, v1 row. Okay, this you will also get from element stiffness matrix 1. Now if you just see this next one, that is u2 row, u2 column, this one specially u2 row, u2 column. From this point there are 2 values you get. One is in stiffness matrix k1 and the other in k2. Okay, you should carefully add those two. Okay, u1 row, u2 row, u2 column. Okay, see here, u2 row, u2 row, u2 column, u2 row, u2 column is this value. That is present here also. And also if you just refer this second this one, u2 row, u2 column is this one, 0.8, and that is 0.512. You have to add those algebraically in this cell, 0.512 and 0.8. Similarly refer all the cells and fill this global stiffness matrix. Okay, after filling this global stiffness matrix, I have just added those values. Okay, that is 0.518, 512 plus 0.8. Okay, and you will end up with global stiffness matrix K. After writing this global stiffness matrix, global force vector F have to be written. F is what we have discussed earlier. F is force vector F1x, F1x, F1y, F2x, F2y, F3x, F3y. Okay, force at node 1 in x direction, force at node 1 in y direction. Just seeing my problem, force at node 1 in x direction is 0, force at node 1 in y direction is also 0. Force at node 2 in x direction is 0, whereas in y direction there is some value called as 12 kilonewton. Okay, but this is in downward direction, you have to write minus 12 kilonewton. Okay, and force at node 3, x direction force is 0 and y direction force is also 0. But if you see carefully, node 1 and node 3, they are fixed. There are reactions generated. So at node 1 there is r1x and r1y. R3x and R3y are similar reactions which are generated at node 3. So for this reason, if I see my force vector F1x, F1y, F2x, F2y, F3x, F2y, they are nothing but my global force vector R1x, R1y, 0, minus 12 kilonewton, 12 into 10 to 3, F3x is nothing but R3x, that is the reaction generated. F3y is nothing but R3y, that is the reaction generated at that point. Now write the global displacement vector q, u1 v1, u2 v2, u3 v3. Okay. Now what is the next step? Step 5 is equilibrium equation. K into q is equal to F. K, global stiffness matrix, is also determined in the previous step. Q, global displacement vector, is also written in the previous step, and global force vector is also written in this previous step. Write K into Q is equal to F. Substitute those values. Okay. Previous problems, that is problems in bars, they were simple. We could write those steps again and again. Okay. Now see here, in step 6 we need to apply boundary conditions. What are the boundary conditions in this? Node 1 and node 3 are fixed. Okay, node 1 and node 3, they are fixed. Means u and v, u1 v1, they are not able to move. U and v at node 3, they are also unable to move. Means u1 v1, u3 v3, they are 0, they are unable to move. Okay, so these are my boundary conditions. Instead of just writing those above matrix again and again, I have just implemented this boundary condition in step 5 only. Okay, step 6 I have written there, but those eliminating those rows and corresponding columns is done in this step only, step 5. That is u1 row is 0 because u1 v1, u2 v2, they are all zeros. So u1 row, v1 row, u3 row, v3 row, u1 column, v1 column, u3 column, v3 column, these all are eliminated now. Okay, then after this I have just written the simplified last matrix, that is after applying boundary condition, what is the reduced size of matrix. I have written it. 10⁵ is common outside. Okay, then that matrix remaining values are written 1.312, 0.384, 0.384, 0.288. Okay, u2 v2 0 and minus 12 kilonewton for force vector. Okay, the method what we have done is, again we have used this elimination method. Okay, that is Gaussian elimination method, that is writing it in an augmented form. First write it in augmented form. After writing it in augmented form, then you do certain row operations so that you convert it into upper triangular matrix. After converting to upper triangular matrix, then do the back substitution. After doing the back substitution, solve for the second row, you will get v2. Solve for the first row, you will get u2. v2 is minus 0.683, u2 is 0.2. Okay, and then nodal displacements, final nodal displacement of this problem are u1 is 0, v1 is 0, u2 is 0.2, v2 is minus 0.6833, that is, it has moved in a downward direction. u3 is 0, v3 is 0. Next, after doing that, we will calculate the strain and stress in each element. Strain is this epsilon 1 b into q. B matrix for trusses is 1 by L minus C minus S CS, u1 v1, u2 v2. Minus C CS values are taken directly from the element table. Okay, 1 by 500 minus C minus S, those values are fed. u1 v1 values are taken from step 7. u1 v1, u2 v2 values are fed, and simplify this matrix, multiply these rows along with this column, you will get strain as minus 4.99 into 10 raised to minus 4. Okay, strain doesn't have any unit. Stress is equal to what? E into strain. Strain for this first element is minus 4.99 and into Young's modulus is 2 into 10 raised to 5. You will get stress in first element is minus 99.99 MPa. Okay, now similarly solve for this strain in second element, again b into q. B matrix for second element becomes 1 by L minus C minus S CS. Second second element values of length, cos theta and sin theta values have to be fed, and displacement associated with it are u2 v2, u3 v3. Okay, take those values and substitute it, and multiply this row along with this column, you will get this matrix. Strain for the second element is minus 4 into 10 raised to minus 4. Okay, and after calculating the strain, stress in that element is stress is equal to E into strain. Young's modulus is 2 into 10 raised to 5 into minus 0.4 minus 4 into 10 raised to minus 4. You will get somewhere around minus 80 MPa stress in that element 2. Okay, next calculate this reactions. After this solving this stress and strain, calculate the reactions. Reaction R1, R2, R3, R1x, R1y, R3x and R3y. Where we have to refer? We have to use this step 5 equations again. Step 5 equation, first row you multiply to this u1, v1, u2, v2 column, you will get R1x. Second row you multiply with this column, you will get R1, R2, R1y. Fifth row if you multiply with this column, you will get R3x. Sixth row you multiply this with this column, you will get R3y. Okay, this step I have written that only. Okay, R1x, R1y, R3x and R3y. Okay, I have multiplied and showed you the value. See the values of R1x, R1y, R3x, R3y. This is that step we can check whether the results what I have got is approximately correct or not. R1x is 15.998 kilonewton. R1y is 11.99 kilonewton. R3x is minus 16 kilonewton. R3y is 0. Now how to check whether they are correct or not? Checking is what the force applied in this problem. If you just remember, the force applied is only in y direction, that to 12 kilonewton. 12 kilonewton in y direction. Now refer your final reaction values. Okay, if you see this R1y 11.99 kilonewton, 11.99 kilonewton positive, that is in upward direction, that's it. Okay, force applied is in downward direction, reactions generated in upward direction, they are equal and opposite. Okay, then our force applied is equal to our reaction generated, and R3 is 0, R3y, that is 0. Okay, that's okay. Now R1x and R3x, if you just refer, R1x is 15.99 kilonewton, R3x is minus 16 kilonewton. They are also equal and opposite, so our system is under equilibrium. Okay, now we'll the problem gets over here. Okay, next we'll discuss about one next problem that you have to do by yourself. Okay, for this same problem you also need to determine the same things, that is nodal displacement, strain, stress in each element, and also the support reactions. Okay, that previous problem you had a step bar like this and the bar was going ahead like this. Now this another bar is going back end. Okay, that's the only difference, rest the problem is same. Okay, 2 bar truss element only. Okay, see this I have given you the element number 1. This is my element number 1 and this is my element number 2. Node 1, node 2, node 3, they are fixed. Okay, you can do the discretion in any way. Okay, if you are interested you can do this 1, 2, 3. But what happens is, while collecting the answers, it becomes difficult for me to correlate. One person takes this as node 1, one person takes it as node 3, one person takes it as node 2. Then the uniformity will not maintain. To maintain the uniformity, I have just given you the node numbers also, 1, 2, 3. These are the nodes, and for these nodes you have to solve. I'll give the hint. You can see this length. Length of the second element again is given, that is 750 mm. Length of the first element has to be determined using this Pythagoras relations. 500 and 750 is the opposite and adjacent side values. Area for first element is 200 mm square. Area for second element is 1000 mm square. Area for first element and area for second element, they are different now in this. Whereas the Young's modulus, they are same. Young's modulus for first element and second element, they are same. Okay, uh, is trigonometric relations to calculate theta. I will tell you what is the value of theta. Theta value for this element 1 is this one. Angle made by this element 1 at its local node 1 when measured in counterclockwise direction. Theta 1 will be somewhere acute angle. You can just see the figure, it will be acute angle. Now what is the angle made by element 2? Okay, element made by angle element 2 at its local node 1. If you are having little bit idea how to determine it, pause the video now only, identify what should be its angle, and then again play it and see what should be its angle. Okay, see here, I'll tell you, angle made by this element 2 will be angle made by element 2 at its local node 1 for that element 2 is 2. Okay, when measured in counterclockwise direction is like this. Okay, so theta 2 will be here, and then what is that value of theta 2? If I keep a protractor here, theta 2 will be 180 degrees. Okay, I have seen students, even though for element 2 local node 1 is 2, they take angle as 0 degrees. No, it is 180 degree. Okay, uh, for those students who have recalled the answer correctly, that is angle as theta 2 is 180 degree, you don't try solving some more problems and try to determine some more angles. And those students who have not understood why that angle 2 came out to be 180 degree, again rethink about it. Okay, and then solve this, and let me know if there are any difficulties. Thank you.